Now we will turn our attention to an important discussion in multivariate GARCH model, which is in GARCH chapter, which is multivariate GARCH model, and there are four types of multivariate GARCH models. The VEC model, which is direct generalization of the univariate GARCH model to multiple dimensions. Then BEC model of Engel and Kronker, and the purpose of BEC model is to reduce the parameter dimension of the VEC model, which will give you a huge degree of parameters, and that has the advantage that VT is restricted, or the GARCH variance, conditional variance, is restricted to be positive definite. Then we have the DCC model, which reduces the dimension indeed of the BEC, so it's an update on the BEC, and also makes estimation of higher dimensional M-GARCH models. Then the DECO model, we'll end with DECO model, that simplifies the DCC model, which is an update indeed, by restricting all correlations to be equal contemporaneously, with the result that estimation is simplified, so the correlations are generally equalized contemporaneously. Kind of DECO model is taking the concept of gradient boosting, so we will see its application in econometrics. We will in this particular example we will look into BEC model, but before that, just to revise the whole thing, we'll just go through BEC very quickly. So if you have n equals 2 variable, BEC is simple increase in dimension to include multiple variables. So VEC is also GARCH, and in terms of two variables, this is the ARCH specification, which we already know, u square t minus 1 n. This is the GARCH specification, which is the lag of this. And in case of n equals 2 variables, we know we have two conditional variances. One is diagonal and the other one is off diagonal. So sigma 1 1 and sigma 2 2 are diagonal elements, and 1 2 and 2 2 2 1 are equal of diagonal elements. So you actually have three elements, despite there are two variables. Because the three elements, our dimensions should match, so constants match, as well as the coefficients are also 3 by 3, giving us a square matrix. Then the vector, this is the vector, which is simply squaring the two residuals, the ARCH parameterization and the GARCH parameterization, and this is lag. So this is simple parameterization, simple representation or specification of the model. And VEC dot, when we have VEC dot, we will see its function. It means the column stocking of all the elements of a symmetric matrix. So you have a symmetric matrix here, right? And when you do VEC dot, we put the symmetric matrix, which is a 2 by 2 positive definite matrix, or whatever 2 by 2 matrix, are stocked together. So basically we'll have 4 elements, but yeah, we'll remove one element so that we get 3 elements. The VEC model does not guarantee that GARCH will be positive definite at each t, and even in the bivariate case there are a large number of parameters, right? So okay, moving on. Basically, when we have a two-dimensional, n-dimensional VEC model, our constant matrix is number of parameters will be n in 10 plus 1 by 2, which is quite high. So you have two variables, 2 into 3, 6 by 2 gives you 3 parameters, right? Very simple. So you have 3 parameters here. See, 3 parameters. Coefficient will be squared, n in 10 plus 1 by 2 whole squared, n in 10 plus 1 by 2 whole squared, so 3 squared 9. So you have 9 parameters, 9, because they're squared. It's very simple representation of VEC. So when you have 3 plus 9 plus 9, you have 21. You add them up. So you have 3, you have 9, you have 9. So you have 21. But when you have 3 variables, obviously that increases highly, and you have 78, and you have 4 variables, the parameters are 210. So this makes it very weird and very unfeasible, so we don't use vec anymore. However, for column stocking we use the vec function. So now comes the one in action. Vec, to impose positive definiteness restriction on our GARCH, multivariate GARCH, we're simultaneously reducing the dimension of the parameter vector. Vec is V, where C is now a lower Kolesky triangular matrix. Okay, so this is with restriction is becoming easier. We have a lower, we have positive definiteness restriction. Our constant has lower triangular Kolesky decomposition. A and D both are n by n matrices. So you have 3 variables, then you have 9 by 9, 3 by 3 matrix, 4 variables, 4 by 4 matrix, and D are 3 by 3 matrices. However, we see there is a decomposition here. So A transpose, because they're positive definite, we're deriving them from positive definiteness. Obviously inversing them is possible. If they are not invertible, then this decomposition will be a failure. So for illustrative purpose, the matrices of the Beck model in equation are now spelled out in case of n equals 1. So if we have n equals 1, in the univariate case, when there is just n equals 1, obviously there is just one standard deviation, one residual, one constant, one coefficient, and we have the Kolesky decomposition. We have this decomposition structure. So C square, A square, because it's a decomposition, everything will be squared, and that gives you a positive definiteness, positive definite matrix. Beautiful, right? When you have 2, 1 becomes 2, so it is a 2 by 2 matrix. Now diagonal and off diagonal elements, we know in off diagonal we have covariances, in diagonal we have variances, we already know it. Then the residual, then the constant. Obviously, because we are talking about in terms of constant, we are column stocking them. Why are you setting this 0? Because they look the same. So this is something, because okay, this is lower triangular representation. Because it's a lower triangular representation, the upper portion is becoming 0. Makes sense. So A and D, the matrix has the form. Obviously now we are just simply decomposing, decomposition with the, it's a decomposition technique. Decomposition technique, very simple, which is simplified. When we just simplify them, just change with the inverse and just writing forward. In case of so before we had 21 parameters, now we have much less parameter in Beck. The number of unknown parameters we can further reduce when we restrict A and D to be symmetric. Okay, if A and D are symmetric, which means they two are equal if the off diagonal elements are equal. If in case they are not symmetric, the off diagonal elements are not equal. When you have off diagonal elements equalized, what do you get? You don't get 4 parameters, you get 3 parameters. If you don't have off diagonal, if you not have a symmetric matrix where the off diagonal elements are different, you have 4 parameters. But generally we do with LR test, we check if the off diagonal likelihood ratio test, we want to see if off diagonal elements are equal or not, they satisfy or not. Otherwise, or we can assume the covariance is constant, and in case of an asymmetric, we can check for if the Beck model is symmetric or asymmetric by setting them equals to 0. So if they are 0, you have symmetric. If they are not 0, you have asymmetric. Simple. It's the same thing actually. You can test for equal or you can test them against 0. So by variate Beck model, that's what we are gonna look into now, where you have 2 variables y1, y2. Obviously that means you have gamma 1 and gamma 2, constants and residuals, and the equation, you know it. So we're gonna have a quick look into it. Log likelihood, we're gonna look into log likelihood and conditional correlation. This is a conditional correlation equation, right? Sigma 1 to diagonal of diagonal element. Constant covariance is between 2 intercepts based on model. So we check if we can reduce the parameter, which means We want to see if covariance is constant or not. They will be constant if the octagonal elements are 0. So this is pretty easy problem, and this is in page 33. Let's go to page 51, and I think this is where, so we remembered we learned a very important program, which is realized variance, which is variance weighted variance, and mean impact curve we didn't go through much, but this is our MV GARCH model, and exercise is based on whatever information was there in 7. The variables are, well, 3-month yield and 1-year yield, two variables, different variables. This is the symmetric back specification that we are just talking about. We want to test for LR if we have constant covariances or not. We want to do LR test to see if we have constant covariance or not. We want to do back model again, but now we want to standardize the T distribution for leptokurtosis. We want to check for leptokurtosis. Okay, so this would be, this beautiful program would be back model. Let's see how back model works. All right. So this is the code, and first we need to see if we are putting a function, additional function. We will certainly put additional functions, but let's see, because we're going to estimate the parameters with the maximum likelihood. So function is, first we need to find the parameters, all the parameters, and y asymmetric, and the log likelihood function for back unconstrained. Back unconstrained meaning that octagonal elements are not 0. So t and n equals size of y. Okay, fine. F is zeros because we're gonna initialize a loop or something. Yeah, f is zeros, t rows and column, size of y. H is covariance of y, initialize conditional covariance matrix, which is the octagonal covariance of y, meaning because we have two variables, so taking the covariance, conditional covariance matrix. U is standard deviation of y, disturbance vector being initialized, so H is covariance of y. All right, and variance multiplied is covariance in that sense. U equals U transpose, residual equals residual 0, and equals U transpose. Okay, because they need to be squared, so their transpose should be the same. So in U we are basically storing the transpose of U. So C is lower triangular matrix, first three parameters. A has 4 parameters, D has 4 parameters indeed. Now let's update the conditional mean. 1 equals 2. So conditional mean is be 12 and 13 columns, 12 and 13 parameters. 12 and 13 element are basically conditional. M will update automatically because 12 and 13 is a two variable, so there will be two conditional mean, right? And when we have two conditional means, let's go back to the page. We were in 42, I guess, right? No, we were not in 42, I'm sorry. Right, just bear with me. Yeah, so we have conditional mean and conditional variance mentioned somewhere here. Okay, let's update conditional means. Oh yeah, so bivariate asymmetric, here should be the means, the gamma hat conditional means should be here, right? This should give us the conditional means. Okay, and here in the code there the 12th and the 13th parameter, we can check if how many parameters we have. We should have how many parameters? Bivariate back model, for that we should have, we just discussed that in a few minutes earlier. In a 2 case we have 11 parameters. because unknown parameters are 11, we are updating the information. So we have mentioned 11 parameters in the code, up until 11 parameters to be estimated, until when 13 parameters will give us conditional mean. Okay, u equals y minus mu, residual minus mu, obviously equal to y minus, this is the conditional mean parameter, gamma 1 and gamma 2, y minus mu, and we are taking the transpose of y. Okay, so we are gonna update the residual. Why are we taking out transpose of y? Maybe y is stored in okay, because all elements in the first column, all elements of all columns, so y1 and y2, we have two u's, we'll have two u's from it, so we are transposing into columns. Then comes the equation of the function, and the function, the log likelihood function here would be log likelihood function here would be, so the function is half log twice pi, half log determinant of h. Let's see, this is log likelihood likelihood ratio. However, the function should be somewhere mentioned in here, right? Let's see. I see in the book the function is not mentioned. Why don't you? No, we don't have the function mentioned in the exercise as well as we can recall. So let's just see. Half log twice pi, half log sigma square, which is our covariance, and u inverse of hu, this is the variance covariance, right? So u transpose u square divided by sigma square, very simple function with unconstrained formula function actually, sorry. And then comes conditional covariance matrix, and that will be updated. CC transpose, as we know, A transpose U, U transpose. Okay, remember U and U is same, so that we get U square. DD transpose H. Why are we not, well, squaring D? Not necessary. There is a possibility because U is a constant in the hence where U and U transpose should be equal. There shouldn't be any difference. Is it a constant? Do we have a constant representation in residual? Let's see what is the residual matrix look like. Yeah, they are actually vectors. They are actually vectors. So when you transpose them, okay, so this is how they should look. The question is, why did I transpose them? In that case, however, it really doesn't matter because the residual E equals residual transpose doesn't work in this equation because it will, this is just to make things difficult. It's not necessary at all. Okay, because this gets inverted, it will give you a matrix. Fine. Then asymmetric back model where the off diagonal elements equal to 0 and you have lesser parameters. So this is understandable, this is understandable, this is understandable. Update conditional mean. However, there is a little change. The change is off diagonal elements are equal. In both cases, off diagonal elements are equal, and you have 9 parameters, unknown parameters. With unconditional conditional mean, you have total 11 parameters. And then we update the residual y minus m. Fine. Depends on the dimension, maybe they're in column or row, it doesn't matter, you can adjust them later. So then you have same equation, just here off diagonal elements are equal. Constant covariance. In terms of constant covariance parameterization, off diagonals are 0, so we have constant covariance, off diagonals are 0. We have even lesser parameters in case of constant covariance. So we have our 3 functions, and that's what it was actually it was expected, because let's see, in our problem. Let's go back to page 51. What do we have here? See, the question suggests you to find a symmetric with restrictions like constant covariance and without constant covariance. So CD3, we have BCD, we have actually 3 functions. Now let's run the functions. Let's go up. First let's load the 2 variables, take the difference, fine. Then asymmetric MV GARCH 1 we are just 1 2 3 4 5 6 7 8 9 10 11 12 13. With the gammas conditional mean you have 13 parameters, unknown is 11, so you just give something to start with and you run the first function and fine, great, you have all the parameters you need. For asymmetric you have 2 less, 1 2 3 4 5 6 7 8 9 10 11. You run it again and fine, and then conditional variance at optimal parameters. Okay, we have in both cases we have the optimal parameters. We want to compute the conditional variance. Is it a question? So we want to estimate the conditional variance with optimal parameters. Covariance of y as it is. Now thetas have been estimated, we put them in C. Thetas are estimated, we put them in, this is same, so at a lesser parameter which is not constant covariance. However, this is restricted model, and let's just, for I equals 1 to t, let's just put it in a loop. Residual are updated, t rows 4 columns, right? And for the 4 columns we have h, standard deviations, estimated u and h, then covariance with I rows for all columns, I rows which is t rows 4 columns, so for all columns h I transpose h, all elements of h are put in stocked together, that gives you covariance matrix. All element of standard deviation is stocked, gives you covariance matrix. If we run it, what do we get? Basically, for covariance matrix, we are running it for covariance, looking for covariance matrix. Beck MV GARCH 1 okay, likelihood ratio, we do it, and LR test for constant covariance, this is the LR test. Now these things we have done so many times, we know it already, we run all the parameters again and again. Is there anything tricky here? Not at all. Nothing is tricky here, is just we take the optimal and find a conditional variance. That's all. So we have a conditional variance with optimal level of information. Then we can look into students t distribution. And what is the change? The change is simply here. You see the log likelihood function changes, that's all, nothing else, only the log likelihood function for symmetric Beck model changes. So it's a very simple code, log likelihood function changes, fine. So we solved the Beck model. Now DCC and DECO model. Now we want to talk about DCC and the DECO model, but before that, before going to that direction, we need to go back to talking about DCC and DECO. So let's move to page 26. So DCC model, the dynamic conditional correlation model, is the dynamic conditional correlation model, imposes positive definiteness on the GARCH residual, and achieves a large reduction in the number of parameters from univariate GARCH together with parsimonious conditional correlation matrix. So with TCC we get an update on our GARCH, multivariate GARCH, and we get a large reduction in the number of parameters by univariate conditional GARCH variance together with parsimonious conditional correlation. So parsimonious conditional correlation matrix. Now this time conditional correlation matrix plays a very important role. And what's the conditional correlation matrix? It's simply of diagonal element divided by root over the diagonal element multiplied. So we have S R S. Remember S? Now we are going to talk about S. This is going to be fun. R is a n by n conditional correlation matrix. S is a diagonal matrix containing the conditional standard deviations. So when the conditional variances are located, we just square the conditional variances. So S is a matrix where everything is 0 except we make it by taking standard deviation. We just put standard deviations diagonally in a matrix. So the conditional variance have univariate GARCH representation. This is univariate GARCH. With univariate GARCH we find variance, you just square the variances and just put them inside the S matrix, the diagonal elements. The specification of conditional correlation R becomes diagonal of root over Q, half is root over, so 1 by Q. So Q diagonal, basically this is a decomposition. So Q inverse, right? So root over 1 by root over sigma square. So this looks like 1 by root over sigma square basically. Yeah. What is Q coming from? I'm not sure. Q has GARCH 1 specification. Okay. So you take GARCH 1 specification, 1 minus alpha minus beta Q be alpha zt minus 1 zt minus 1 transpose. Z is standardized residual. So many things. First we need Z, which is a standardized residual. We estimate it with V by sigma. I find standardized residuals first. And then with that you find Q, so which is given by Q, right? Q is the factor. So Z square, so Z, I mean you take all the standardized residuals and you basically make a matrix out of these standardized residuals, kind of like a variance decomposition matrix. All right, now that makes sense, right? It's a variance decomposition matrix of standardized residuals that gives you Q and dash hash. You use the Q hat and you find Q. Then you put the Q in R. So you take the diagonal elements of Q. You take the inverse of the diagonal element of Q, which represents the variances, and just you take the standard deviation and simply Q. Okay, here comes our M GARCH Bach. Okay, see M GARCH Beck model where we have conditional covariance, conditional correlation. This is how it looks. Variance for 3-month, 1-year rate. Fine, good. We have done it already. So this is M GARCH V for the 3-month rate, and this is from the regular one, from the regular estimation. When we did update our conditional covariance, this what it gives. Updated conditional covariance gives us. We just take the columns and plot them. That's all. 1-year rate, conditional covariance, conditional correlation matrix. So conditional correlation and the conditional covariance. C, conditional covariance, where we estimate the parameter again This is GARCH, as we can recall. What is this one then? Just have a look. Constant covariance. Condition also generate graph. Variance of 3 months. Covariance matrix. We found the covariance matrix. We're just plotting the covariance matrix. 1, 2, 3, 4. Conditional covariance is okay, fine with me. 3 covariance matrix, all rows column 2, column 1, column 4. So which means, okay, H, how is it stopped in H? H gives you the variances and the covariances. Oh sure, now I understand, because H will give you variances and covariances, right? Let's have a look into H itself. Conditional covariance is this diagonal element. So 1 and 4 are variances, 3-year rate, 1 year, 3-month rate, 1 year rate variances, and this is the 4th column, which makes it third column the correlation. No, 4th column is correlation. And conditional covariance. Conditional correlation is okay. Conditional correlation is estimated. Yeah, obviously, conditional correlation is estimated and plotted. Oh, great. So quite easy, simple. It's basically 3-year rate, 3-month rate, 1 year rate, and this is this one. Conditional variance, covariance, and conditional correlation is estimated with the correlation equation, if you can recall. Okay, and conditional correlation equation, we know what it is already. We studied that. This is the conditional correlation equation where numerator is covariance divided by root over variances squared. So let's get back to what we are talking about. Then we put the decomposed Q hat here, 1 minus alpha. Then we find R, conditional correlation matrix, where Q divided by diagonal elements. This is looks kind of the same, where Q is what we call the conditional covariance and divided by root over variance. Yeah, makes sense basically. Now R, this is R, and we need R and we need S. These two S's are, S is GARCH and diagonal square root of GARCH is S and S. So this is your DCC model. So I'll look into a bivariate DCC model when you have 2 GARCH. So obviously take 2 standard deviations. Then we start with the standardized residual. To find standardized residual, what do you do? In general, we take error by standard deviation, U by S. Fine. In a matrix case, U error by standard deviation matrix. We use the standard deviation matrix, and this is how it looks. Then we compute Q, which is the correlations of 1, 1, 1, 2, 2, 1, 2, 2, which is coming from the residuals. So we actually multiply them together, right? Z1, Z2, if you have 2 of them, how can you make a matrix? Probably you do ZG transpose, that's all, and that gives you conditional covariance. So Z2 square this one multiplied, this one, and for t equals 1 to t, and then you have conditional correlation. The relevant equations are 1 minus alpha minus beta c q. Now let's see how this equation is represented. This equation is represented this, where we use the correlation, we use the z's, lagged z's, and we use the lag q, and then we, okay, step 3 is computing q. We have elements of q, we construct the matrix of conditional correlation R with q. So now, okay, which is the, so this step is coming from diagonal q, q diagonal q. Quite interesting, because what I am confused here is in this portion q. Okay, so this is again GARCH equation, then it's just diagonal and the whole matrix and diagonal, and gives you R, and V is, you take R, multiply with that SS, and 1 row 1 2 row 1 2, so you have R, you have V. This is a conditional covariance matrix looks like. For small n, maximum likelihood estimation, this is the maximum likelihood function. Half log test by half log in case of sigma square with SRS. Obviously the decomposition, I'm fine with that. AB is AB inverse, AB inverse, A inverse. We can do B inverse, A inverse, so we can break it down more. Half log test by half log S square, half log R, half log Z transpose RZ. So now this is more broken, right? So you have AB or B inverse, A inverse, 2 log S plus log R, something like that. Okay, so we're going to use that equation. And then Z is standardized variable, where Z is V by S. ZZ transpose is something we do further modification, and maybe we have V, S square V. The full log likelihood function is theta 1, theta 2. Let's see, gradient and Hessian is automatically estimated, so the function will cause us a bit of trouble. Page 37. Let's see DCC. The data is there, LR test we want to do. So we want to do DECO and DCC both. So let's start with the DCC. 5342. Okay, let's start with DCC. It's gonna be a bit difficult this time. I hope it's a bit difficult. Okay, let's see. Maximum likelihood estimation is gonna cause us a little bit of trouble. Back is fine. We don't need this one. Let's DCC. Let's look into the log likelihood function first. So neg log GARCH by likelihood function, half log test by half log standard deviation, half log Z squared, right? Half Z squared, which means there is some log likelihood function where there is half Z squared. Here makes sense. Z is S inverse V, right? V by S. So you have V by S transpose, which means Z squared or ZT, right? So 2070, we use this code. Yeah, the final code, this one. Let's change the color. Yeah, this is a waste of time. So this is the equation. Okay, let's change the color. Oh, I can't see anything from here. And let's see. Yeah, so we have half z squared it. So h, standard deviation, is the question. So beta 1 normal, cumulative distribution beta 2 trimmer. So norm CDF beta 2 trimmer, standard deviation u, norm CDF beta 3. So norm CDF, let's see the function. For some reason it's not coming, or it seems like it's coming. I'm just gonna pause it and let it come. So we were talking about normal cumulative distribution function. What is the use of normal cumulative distribution function? It gives you a confidence bound for the distribution using a normal approximation. So when you have high sample size and you want to estimate mu, standard deviation, and covariance, variance covariance, basically peak of, which gives you covariance matrix of the estimated parameters is peak of, and alpha gives you the confidence bounds. This allows you the confidence bound for your variance actually. So that's great. And so we want to recursively estimate beta 1, which is in our case recursively estimate, we are estimating h here, right? Beta 1 is the alphas, right, in each case, and we want to estimate, we want to do a normal cumulative distribution function, and we want to estimate mu, sigma, and whatever. So beta 2 trimmer u square, adjusting the dimension. So mu is beta 2 multiplied to the residual. Mu is beta 2, right, multiplied to the residual. Where is our mu? I'm trying to find some answers from here. Okay, I think we missed a few points. Gradient Hessian, we didn't go through the whole chapter. You see, for unknown parameters 3n plus 2, we need 3n variables and 2 alpha and beta correlation parameters. As with the big model, small values of n, we can use iterative estimation, where the unknown parameters is 3n plus 2, where 3n is the GARCH parameters, alpha and beta are correlation parameters. So we need to find alpha and beta. So two-step iteration process. First is the volatility parameter. We need to solve the log likelihood function to find, this is simply the product of the diagonal elements. The log likelihood function in equation decomposes into n separate components and correlation parameters. Maximizing of GARCH parameters. Z does not contain theta expression to maximize simply this. So this needs to be maximized. Correlation parameter and volatility parameter are estimated with this. two-step response but not asymptotically efficient, and this and that and this and that. This is quite huge, the DECO model, the DCC model. Okay, let's have a look into the code. And square and the normal cumulative distribution function of beta 3. So mu, sigma, and peak of covariance matrix. The variance mean is beta 2 constant, then beta 2 sigma square. I'm getting stuck in somewhere. I'm sorry, my voice is not yeah. Okay, I'm getting stuck here. What is the equation? Mu mu sigma square variance and covariance, right? Mu sigma square variance and covariance. Mu, where is V? This is really difficult. Okay, let's just go through it. Let's see what they have to offer. GARCH 1 U mu sigma and peak of Z is U by square root of H, which is sigma square. So constant, mean, square, residual, square residual, then variance. Okay, Z square, fine. Correlation component of DCC, BYH1B, normal cumulative distribution function. F zeros y u y z is what we know. Q bar, z transpose divided by t. We learned that Q bar z transpose divided by t, very simply proposed. Good. Diagonal matrix of the conditional standard deviation, diagonal of square root of h. So we have h estimated and square root of h. We have diagonal, you have s, 500 s. Good. Conditional covariance matrix, correlation matrix is inverse of diagonal of square root of diagonal q. We already know it. R is TMP, Q TMP, fine, we already know it. Function is half log determinant of R, half Zi inverse. So this is the decomposition with this equation is basically which one? Yeah, this one. Half Z over half ZZ. Same thing. Update Q. 1 minus beta 1 minus beta 2. So where is 1 minus beta 1 minus beta 2? We also saw that equation. Just wait. Here you go. 1 minus beta 1 minus beta 2. B1 Z1 Z transpose B2Q is the same equation. Fine. Okay. Full likelihood for dy. Constant conditional covariances. Okay. Rex error B1 B2 trimar. Fine. Rex error. Why not x? Why not x a? Why not x and a? Or x, why not a? Mu initial y is the residual and comes a. X y not x a, x y not a, x y not initialization and a. So So full likelihood for DCC model is gonna be quite difficult. Then what do? Optimize, run the optimization function, start, and I'm kind of lost again. Here is the function running, 3 rows and column, 3 rows and column. Yeah, I think I'm gonna take a break because this is really difficult. So many information here actually. Number of parameters are 3 rows and column. All right, yeah, 3n plus 2. 3 rows and column, 3n plus 2, alpha and y. Fine, now that makes sense. B start is initialization. Here is start deviations are located. Then we do mu, then the variance, then covariance gives you this, bound. MV GARCH, run it, you get H1, all rows k columns. So these are the GARCH parameters. Beta 1, 2 and 3 are GARCH parameters. Correlation components are estimated and presented. This is really difficult. I think I need to revise it several times to understand properly. I could not, I guess, properly understand what's going on in this code. So at this stage I'm gonna just bring it to stop and let's see.